Hello everyone. I want to give you a quick demonstration of a video point and how you're going to use it this coming week to study projectile motion. Now, if you remember, you used this with the Moon Man video, but not in a very sophisticated way. So I'm going to show you a few extra techniques. So when you come into the lab, I'll get you to fire up video point like before. So if you just notice what I did, hit the little blue dot. You can close this frame. You can open movie. And the movie I've already made for you. It's actually called Tuesday Class 1. Where you'll find it is it's going to be on your desktop. This video, Phys Video folder will be on your desktop, so you're going to go in there to find it. If that changes, I'll tell you about it on the day of the lab. So you open this, and here it is, and you can just hit OK. This here means essentially that there's just one ball in the frame, and you can do this. And if I go up to movie, and we had to do this with the Moon Man, you want to go down to movie and turn off this play all frames, which seems backwards. You can hit go, and you can see the ball tossed. And this was a video that was made actually last year in our lab. It's a real, that's a ball bearing. That's a human hand, obviously. It's just a little toss, and it's tossed right over this ruler. And I've got some lights on so you can see everything. Now, how do we use this stuff in a meaningful way? One of the things you want to do, and in fact, I'll point out one thing. Notice that there's a ruler in here. Unlike the Dave Scott Moon video, he didn't have a ruler. We do have a ruler in here so we can scale things, and we're going to use this. This ball, though you can't exactly tell, has been thrown right over this ruler. So that ruler is just as far away from the camera as is the ball. So what I'll get you to do when you have this fired up is you'll go to Edit and select Hide, Leave Hide Trail. And then bring this cursor down, put it on top of the ball, and click your leftmost button. And see it leaves a dot where the ball was, and it advances it. It advances it by 1/60th of a second. The camera used to take this video takes 60 pictures a second, or one every 1/60th of a second. You can keep doing that. Go up, click on it again, and it advances it again. And notice the time has gone ahead by another 1/60th of a second. And do this, and you can keep doing this. Now, I want to stress when you're doing this in the lab, you want to take some time out to do this. If you're sloppy, suppose I get the corner of the ball and I do this, and then I do this corner here. Notice your dad is going to tell you that the ball was doing the zigging and zagging, when in fact it wasn't. It's just I was being sloppy. Now, if you do something like this and you feel you didn't click on the ball in an appropriate spot, you can hit a backspace button, and notice how the dot will sort of get double highlighted. I can now hit delete and get rid of that. I can backspace again and delete that one, and I can start again. So you can just back up with the backspace key. I'm using, although you can't see this, I'm using the sort of up, down, left, right arrows. So I'm using the back and forth arrows, not the backspace, but the back arrow. Again, I can delete that one, and I come over here, and I should be able to start clicking through again, and I can do that. So that's how you can delete. You can just back up and get rid of it. Now this is actually the video you're going to use on the day of the lab. I don't want to do all of it for you. So I'm just going to do a couple of dots, but I want you to do all of them. This ball will arc over here, and you'll probably get about, I don't know, 20 to 30 data points. Now the next thing you do, once you've done that, is you do have to give the movie a scale. Because other than the hand, If it wasn't for this hand in here, you really wouldn't know anything about the size of this ball. It could be very big or very small. In fact, you couldn't tell. It could be a planet going through there for all you know. So what you have to do is you go up to movie and you go to scale movie. Now this distance along the ruler these are two pieces of paper that I've taped onto a ruler. The inner edge of this piece of paper and the inner edge of this piece of paper are 20 centimeters apart. And this ruler will be in the lab, and you can take a look at that. So up here, when you say known length, you're going to type in 0.2. And you'll hit continue. Now what you do is this little cursor, you bring it down with your mouse, and you put the horizontal part of this sort of bullseye thing right along the paper ruler transition. Click on there, and then come down and do it on the other piece of tape, on the inner transition area. And notice that there's this line here. And you have just told the computer that this distance is 20 centimeters, or 0.20 meters. That now allows the computer to give distance to this stuff here. So the camera has provided a timing between points. Now you've told the computer that, you know, this much space here is so many meters, and this much space here is so many meters. Now once you've done that, most of the technical stuff is out of the way. You can go up. You can go up to view, and you can go to new graph. And to do today's experiment, or the one that you're going to come up and do next week, is you really have to study different graphs. Notice here, this is horizontal axis, which you're going to have time. So you don't have to change that. You're going to make graphs of x position versus time, and y position versus time, and velocity versus time. So that doesn't have to change. Point S1, that's just what they're labeling your ball, so you don't have to change that. Here you can toggle between x component or y component. You can even go to magnitude and angle, but we're going to use x component and y component. Obviously x is the horizontal stuff, and y is the up and down. And notice for relative, notice over here there's an origin, and it's already put it in here for you. You could move that, but that's a convenient spot for it. So if you do something like, say, y component, and you want to look at velocity, once you hit OK, it will now make a graph of the y velocity as a function of time. And this is just the velocity in the y direction. So you hit OK, and here you go. And this doesn't look like much, and it's because I didn't take a lot of data, and I didn't take it particularly accurate. But if you look here, you'll see it's v underscore y, so that's velocity in the y direction, and this is time. And you can look at the time. We're talking tenths of seconds here. And we've got distances here. Again, kind of going from about 2 meters to almost 3 meters in the y direction. And that's probably fair. The ball went over about this distance. So you have this. And a really powerful part of this is you can go up to fit, and you can fit an equation to this. Now this doesn't look like much, but if you had data here that really looked like a straight line, you could say, let's fit a linear equation to it, and you can hit apply. If this data, say, was curved, and it looked like some sort of quadratic or power function, you could go down and you could choose polynomial, and it sort of order fits, so it does something raised to the 2. You can go all the way up to 3. We're actually going to plot some stuff that only goes to the square. So you can hit that. So here's a case where my data looks probably a bit linear. I'll hit apply, and it does the best fit line through there. This pink line is your linear equation, and there you have it. In a mathematical form, it's telling you Vy is equal to 7.9 times t plus 3.04. So this is the equation of a linear line, where that is the intercept and that is the slope. And particularly this slope business, depending on what you've graphed, whether it's velocity versus time or position versus time, you want to interpret that on a physical level, and that's something that you're going to have to do in the lab. I don't want to say too much here. I don't want to rob you of your education. I want you to think a little bit about it. But if you've got a velocity versus time graph, I want you to think about what's the meaning of the slope. Here's the number, and this software doesn't know anything about physics. Hopefully you do. So you look at this number. This is the slope. What's the meaning of the slope? And same deal if you have position versus time and you fit it to a linear line. What do you get? On the day of the lab, we are gonna look at some stuff that is interesting types of curves that'll be slightly more complicated equations, and there's a few other things I want you to extract out of that. In any regard, that's how you do that. That's really the main thing. You want to collect your data points. You want to do it very accurately. If you feel you haven't clicked very well on a dot, you can use the back arrows to cancel it and start again. When you get to that point, get all your data and you want to graph things, you can simply go to View, a New Graph. And as I've already mentioned, you can plot X components or Y components. You can do position, velocity, or acceleration. I believe in the lab we're just going to be looking at position and velocity. One thing to keep in mind is velocity and acceleration are built from the raw position data. Every time any uncertainties you have in your position data actually kind of build themselves up slightly worse when you go to velocity, and even slightly worse when you get to acceleration. So the more information you can get out of the basic graphs, such as position, is to your advantage. You can go one more step and your data probably is going to look quite so good, but you can still get some stuff. Sometimes when you're up to this sort of third step, second step, your data can look a little awkward. So again, we're going to work with these two here. And I'll mention these things here don't have to change at all. It's just here you're going to play around with it. And in the experiment, when it says calculate such and such, calculate is probably too strong of a word. It really means to build these graphs and extract out the information from the work that the software package does. So it does a lot of the hard work for you. You just have to interpret what's going on. So anyhow, that's how this works. So hopefully review this once or twice and you'll be ready to go when you pop into the lab next week. So there you go. Hopefully that works out good for you guys. I'll see you later.